In the winter of 1796, a labourer's son sat at the University of Göttingen, 18 years old, and could not decide what to do with his life. Carl Friedrich Gauss was gifted enough to become one of the great scholars of ancient languages, and gifted enough to become a mathematician, and the needle between the two would not settle. His father laid bricks and kept the accounts for a funeral fund. His mother could barely read. No one in that family had ever had a life of the mind to hand him as a map. And then, one morning near the end of March, before he had even gotten out of bed, he saw something no one had seen in 2,000 years. He saw how to draw a shape that had been frozen out of geometry since ancient Greece. But what he had really found was stranger and colder than a new shape. He had found the exact edge of what geometry is allowed to be, the hidden law that quietly decides which shapes can ever be drawn and which are forbidden forever. And almost all of them, it turns out, are forbidden. Tonight we follow that one morning all the way down. Euclid's list, frozen for 2 millennia, a secret diary that lay unread in a drawer for 100 years. Euler quietly breaking a number Fermat had sworn was unbreakable. A young Frenchman who proved which shapes are impossible, and then worked himself into the grave at 33. The 5 strange keys that unlock every drawable shape there is, and a tombstone that had to be carved as a lie because the truth, drawn honestly, looks like nothing at all. By the end you will understand something almost nobody gets told. In mathematics, impossible is permanent. It is proven, it does not expire, and almost everything real sits on the far side of it, walled off for good. Before we start, get comfortable and stay to the end, because the last thing this story does is take that quiet spring morning and turn it into a question no one alive can answer. If you get something out of these deep dives, the real way to keep them going is over on our Patreon, Meridian Labs, the Patreon behind this channel and a handful of others like it. Members get every episode ad-free across all of those channels, early access before anything goes public, and exclusive deep dives you will not find on YouTube. Subscribe or join if you have not. Let's go back to where this began. There is a shape you cannot draw. It has 7 sides, all equal, all the same angle, a perfectly regular 7-sided figure, and you cannot draw it. Not you specifically. Nobody can. No architect, no engineer, no machine, no supercomputer, no alien civilization 1 billion years more advanced than ours. Given only the 2 oldest tools in mathematics, a compass and an unmarked straightedge, a regular 7-sided polygon cannot be constructed. Ever. And I do not mean it is difficult. I do not mean nobody has managed it yet. I mean it has been proven, with the same certainty that says 2 and 2 make 4, that a perfect regular 7-sided figure is forbidden. The rules of the compass and the straightedge do not allow it. And they never will. Take a second with that, because it is stranger than it sounds. You can draw a triangle. 3 equal sides, no problem. Euclid did it on the first page of his first book. You can draw a square. You can draw a regular pentagon, 5 equal sides, and it takes a little work, but it comes out perfect. You can draw a shape with 15 sides. Your intuition, reasonably, tells you that 7 should sit somewhere in there, between 5 and 15. A little harder than a pentagon, a little easier than something bigger. Just a matter of patience and a steady hand. That intuition is wrong. And it is not wrong by a little. 7 is not hard. 7 is impossible. 9 is impossible. 11, 13, 14, 18, 19, 22, 23, all impossible. If you sit down and ask which regular polygons a compass and straightedge can actually produce, the answer is not most of them. The answer is almost none of them. The shapes you can draw are a thin scattering of exceptions in an ocean of the forbidden, and the line between the two, the line that decides which shapes are allowed to exist under these rules, and which are locked out forever, is not a line about geometry at all. It is a line about numbers. A hidden law sitting underneath the whole of elementary geometry, quietly deciding what is permitted. And for 2,000 years nobody knew the law was there. The person who found it was 19 years old. That is the number you will see everywhere, in every retelling, on every plaque. A teenager solving in a single morning a problem that had sat untouched since ancient Greece. It is a good story, and most of it is true, and one small piece of it is wrong in a way I will come back to, because the way it is wrong tells you something about how these stories get sanded down before they reach you, but the core of it happened. In the spring of 1796, in a town in northern Germany, a young man woke up, and before he had even gotten out of bed, he saw how to draw a shape that no human being had ever drawn correctly in the entire recorded history of mathematics. A regular polygon with 17 sides. And here is the part that should stay with you. Drawing the 17-sided figure was not the discovery. It was the symptom, because the same insight that told him 17 was possible also told him, buried in the logic, exactly which shapes were impossible. All of them. Forever he did not just add one new shape to Euclid's short list. He found the machine that generates the entire list, the complete and final catalogue of every regular polygon that can ever be drawn, and the machinery that permanently excludes all the rest. And when you turn the crank on that machine and follow it all the way out, it tells you something that almost nobody who repeats this story ever mentions, because it is the uncomfortable part. It tells you that the list of these shapes may already be complete, that there may be, in the entire infinite ocean of numbers, only a handful of keys that unlock a new drawable shape, and that the last one anybody has ever found was locked in place before George Washington finished his second term as president. No sixth key has turned up since, and there is a real serious mathematical argument that no sixth key exists anywhere at all. That is the question underneath everything I am about to tell you, and I want to put it in front of you now so you can feel it tightening as we go. How many of these shapes are the rules of geometry willing to allow into existence? Is that number final? And if it is final, then a spring morning in 1796 was not the beginning of a new chapter in geometry. It was very nearly the last word. Let me show you how the wall got built, who found the door in it, and what he saw on the other side. To understand why any of this was frozen for so long, you have to go back to the man who wrote the rulebook, because he is the one who set the boundaries that held for the next 2 millennia. Around 300 years before the Common Era, in Alexandria, a mathematician named Euclid assembled 13 books that would become the most successful textbook ever written. The Elements. For more than 2,000 years it was the second most printed work in the Western world after the Bible, and it was not a collection of results so much as a machine for producing certainty. You start with a handful of definitions and 5 postulates, statements so simple they feel like they cannot be argued with, and from those you build, step by lockstep, everything else. Nothing is assumed, everything is earned. And in the 4th book of the Elements, Euclid did something very specific. He showed how to inscribe regular polygons inside a circle using nothing but the permitted tools. He gave you the equilateral triangle. He gave you the square. He gave you the regular pentagon, which is genuinely clever and involves the golden ratio hiding inside the construction. He gave you the regular 15-sided figure, built by cleverly combining the triangle and the pentagon. And he showed that once you have any of these, you can double it, bisect every angle, and you go from a triangle to a 6-sided figure, from a 6 to a 12, from a square to an 8 to a 16, from a pentagon to a 10 to a 20. The doubling never stops. You can keep halving forever. The list Euclid left behind looks like this: 3, 4, 5, 6, 8, 10, 12, 15, 16, and all the doublings that come off them. And then nothing. That was the whole catalogue, and the thing you need to sit with is what happened next, which is nothing. For the next 2,000 years, that is where it stayed. Not because people were not trying. Some of the sharpest minds in human history looked at the regular 7-sided figure, the heptagon, and tried to construct it. They failed. They looked at the 9-sided figure. They failed. And slowly, across centuries, a kind of quiet consensus settled in. This was the edge. This was as far as elementary geometry went. The tools had been fully explored, the map was complete, and the blank spaces on it were simply where geometry ended. Gauss himself put it plainly, years later, when he wrote about his own discovery. He said that geometers had long asserted that beyond those few polygons, and the ones you get by doubling them, there was nothing else that geometric construction could reach. He called it astonishing, in his own words, that although the division of the circle into 3 and 5 parts had been known since Euclid, nothing had been added to that knowledge in 2,000 years. 2,000 years of the best mathematicians alive, and the list did not grow by a single entry. Think about how strange that is. Whole fields of mathematics were born and matured in that span. Algebra was invented. Calculus was invented. And this one small ancient question, which shapes can the oldest tools draw, sat there untouched, apparently closed, apparently finished. But it was not finished. It only looked finished. And to understand why it looked finished, and why the people staring at it could not see the door, you have to understand exactly what a compass and straightedge are actually doing, because the answer is not what you would picture. The image in your head is probably drawing. Curves and lines on paper. The tools are much stranger than that. They are, if you look closely, a machine for doing a very specific and very limited kind of arithmetic. And once you see that, the whole 2,000-year wall suddenly makes sense. Here is what the tools can do, and this is the entire list. There is nothing else. A straightedge lets you draw the straight line through 2 points you already have. A compass lets you draw a circle, centered on a point you already have, passing through another point you already have. That is it. Those are the only 2 moves. Everything in the elements, every construction, every proof, is built from just those 2 operations repeated, and from the new points that appear wherever your lines and circles cross each other. You start with a couple of points. You draw lines and circles. Where they intersect, you get new points. You draw more lines and circles through those. And you keep going. Now here is where it stops being about geometry and starts being about something much deeper. Say you start with 2 points and call the distance between them 1. A single unit of length. The question of which shapes you can build turns into the question of which lengths you can build, which distances you can reach by drawing lines and circles starting from that 1 unit. And when you work out the arithmetic of what those 2 operations actually do to numbers, you find something remarkable. Drawing a line through 2 points and finding where it meets another line, that is arithmetic you already know. It lets you add lengths. It lets you subtract them. It lets you multiply and divide them. Every fraction, every ratio you can build out of your starting unit, the straightedge and compass can reach. For now, ordinary enough. But circles do one more thing. A circle is the set of points at a fixed distance from a center, and the equation of a circle involves a square. And when you intersect a circle with a line, or a circle with another circle, and solve for where they cross, that squared term forces you, at the crucial moment, to take a square root. That is the one extra operation the compass smuggles in, that the straightedge alone cannot. The square root. And that, right there, is the whole secret. That is the hidden law that governs everything. Because it turns out that a length is constructible, buildable with these tools. If and only if you can reach it from your starting unit using only 5 operations: addition, subtraction, multiplication, division, and the square root. Nothing else. No cube roots, no fifth roots, no exotic functions, just those 5 in any combination nested as deeply as you like. Square roots inside square roots inside square roots, sure, as many layers as you want, but every layer has to be a square root. The moment a number can only be reached by something outside that list, a cube root that cannot be simplified away, say, that number is unreachable. No construction will ever produce it. Not because the construction is hard to find, because it does not exist. It cannot exist. The tools physically cannot generate that length, any more than addition can generate a number bigger than its inputs allow. And this is the thing every geometer for 2,000 years was standing right next to without seeing. They were treating the question as geometry, as a matter of cleverness with arcs and lines, of finding the right sequence of moves. It was never that. It was a question about numbers hiding inside a question about shapes. The regular 7-sided figure is impossible not because nobody drew the right arcs. It is impossible because building it requires reaching a length that lives outside the world of nested square roots, a length you can only get to through a cube root that will not collapse into anything simpler, and no compass on Earth or anywhere else can perform that operation. The wall was never a wall of skill, it was a wall of arithmetic, and you cannot climb a wall of arithmetic with a steadier hand. I want to stop here and correct something, because we are now past the point where the surviving version of this story usually starts lying to you, and the lie is worth catching. You have probably heard, if you have heard this story at all, that Gauss drew the 17-sided figure. He did not. He never drew it. What Gauss did was prove through this arithmetic of reachable numbers that it could be drawn, that the length you need to build it lives safely inside the world of nested square roots. He produced the proof, not the picture. The first actual explicit construction, the physical sequence of arcs and lines you would follow to draw the thing, came years later from other hands, and the elegant version most people reproduce today was worked out almost a full century after Gauss, in 1893, by a man named Herbert Richmond. This distinction matters more than it seems, and it will matter more as we go. Because the entire story you are being told is a story about the gap between what can be proven possible and what can actually be drawn. Gauss lived on the side of proof. He showed the door existed. Walking through it was somebody else's job. And here is the second correction, the one about the number 19. Every version of this story tells you Gauss was 19. It is on the plaques, it is in the headlines. He was not 19. Carl Friedrich Gauss was born on the 30th of April, 1777, and the morning he saw the construction was the 30th of March, 1796. Do the arithmetic, and he was 18. 1 month almost exactly from his 19th birthday, but 18. It is a small thing. It changes nothing about the mathematics, but I point it out because it is a clean little example of the way these stories drift as they travel. 19 is a rounder, cleaner number for a headline than 18 years and 11 months, and so the number that gets repeated is not quite the true one, and nobody bothers to check, and the small false version calcifies into the official version. Hold on to that habit of drift, because the deepest thing in this whole story, a part almost nobody tells you, got lost in exactly the same way. Sanded down. Simplified. Made comfortable. Until the uncomfortable core disappeared. Let me tell you about the young man himself, because the arithmetic did not come from nowhere, and the person it came from is stranger and more human than the marble bust version. He was born poor. Not romantically poor, actually poor, in Brunswick, in what is now Germany, to a father who worked as a bricklayer, a gardener, a labourer on the canals, whatever paid, and who kept the books for a local funeral fund on the side, a hard man by most accounts, practical, suspicious of anything that was not manual work. Gauss's mother could barely read. She was sharp, sharper than the father by every indication, and she lived to 97, most of those final years in her famous son's household, but she came from nothing and expected her boy to come to nothing more than a trade. There is a story, and like all the Gauss childhood stories, it has been polished until you cannot quite trust the shine on it, that at the age of 3 he watched his father adding up a column of wages, working out the weekly pay for the men under him, and the toddler piped up that the total was wrong. And it was. The child had followed the arithmetic in his head, faster than the grown man doing it on paper. The most famous of these stories is the one you may already know, the one about the schoolroom. Gauss is a boy, 7 or 9 or 10 depending on who is telling it, and the number itself drifting the way these numbers always drift. The teacher, a man named Butner, wants to keep the class quiet, so he sets them a punishing busywork problem. Add up all the whole numbers from 1 to 100, 1 plus 2 plus 3 all the way up, a task designed to eat an hour and produce silence. And almost immediately, the boy walks up and puts his slate on the desk with a single number written on it. 5,050. The correct answer. He had seen in seconds that if you pair the numbers up, 1 with 100, 2 with 99, 3 with 98, each pair sums to 101, and there are 50 such pairs, and 50 times 101 is 5,050. No adding, just seeing. The teacher, the story goes, was so unnerved he bought the boy the best arithmetic textbook he could find, and soon admitted the child had gone past anything he could teach. I tell you these stories knowing they have been embellished, because the embellishment is part of the point. This was a mind that frightened people. That is the consistent thread underneath the polished anecdotes. Not a hard worker, though he was that. Not a clever student, though he was that too. Something closer to a different kind of instrument, one that saw structure where other people saw only the surface. And a local duke, the Duke of Brunswick, heard about the boy and did the thing that changed everything. He paid. He funded the education of a labourer's son, sent him to the good schools, and eventually to the University of Göttingen, which is where our young man was. In the winter of 1795, going into 1796, when the thing happened. And here is a detail that decides the whole shape of his life, and it is genuinely close. At 18, Gauss had not decided to be a mathematician. He was seriously, actively torn between mathematics and philology, the study of languages and ancient texts. He was gifted at both. He could have become one of the great classical scholars of his century. The needle was truly balanced, and the thing that tipped it, by his own account and the account of everyone who knew him, was the 17-sided figure. It was this discovery, this specific morning, that made him choose. He said afterward that it decided him for mathematics. The entire subsequent career of the man many people will tell you is the greatest mathematician who ever lived. The work on number theory, on astronomy, on magnetism, on the shape of space itself, all of it hung on whether a torn 18-year-old happened to crack a 2,000-year-old geometry problem before he had to declare a major. He did. And the needle fell. We know the date because he told us, and because of a small notebook that is one of the most remarkable documents in the history of science. On the 30th of March, 1796, Gauss began keeping a private mathematical diary, a little journal in which, over the next 18 years, he jotted 146 short entries, most of them a single cryptic line. Recording his discoveries as he made them, he never showed it to anyone, he never published it, and the very first entry, the one that opens the whole notebook, is the 17-sided figure. In Latin compressed almost to a code, it records the principles on which the division of the circle rests, and its geometric divisibility into 17 parts. Entry number 1. The thing that made him. The diary itself has a fate that should make you a little uneasy, given everything I have been saying about how these stories get lost. Gauss died in 1855. The diary was not published in his lifetime, and after his death it sat, unread, among his papers. It was misfiled, essentially, forgotten for over 40 years, the single most intimate record of how the greatest mathematical mind of the age actually worked, simply sat in a drawer, and nobody looked. It was not found and recognised for what it was until 1898, more than a century after that first entry was written, when a mathematician named Paul Stackel came across it. And it was finally brought to light and published by Felix Klein. 102 years the world waited to read entry number 1, and it waited by accident, because nobody knew what they were sitting on. Remember that the deepest truths in this story have a way of getting locked in drawers. It is going to happen again, and the next time it happens to a person, not a notebook. There is a shadow over the patronage too that fits the pattern of this whole story, where the people who make the truths possible tend to come to hard ends. The Duke of Brunswick, the man who reached down and funded a labourer's son, who paid for the schooling that put Gauss in a position to have that morning at all, did not have a gentle exit from history. He was a soldier as well as a patron, and years later, in 1806, in his 70s, he commanded Prussian forces against Napoleon at the Battle of Jena and Auerstedt, and he was struck in the face by shot, and mortally wounded, and died of it not long after, his lands overrun. The protection that had shielded Gauss's early life collapsed with him, and it is a small, sharp irony that the man whose generosity made the 17-sided figure possible was destroyed by exactly the kind of brute historical force that mathematics, in its permanence, is supposed to stand outside of. The theorem is eternal. The Duke who paid for it bled out in a field. The truths survive. The people around them, again and again, do not. And I want to be clear about how far ahead of everyone Gauss actually was, because the 17-sided figure can sound like a lucky isolated trick, and it was nothing of the kind. It was one visible outcropping of an enormous hidden structure he was building underneath. A whole new theory of how numbers behave when you divide them and take their remainders. The theory he would lay out in the Disquisitiones Arithmeticae. At the centre of that book sits a result he loved so much he returned to it again and again across his life, proving it in multiple different ways. A deep and surprising law about which numbers are and are not perfect squares when you divide by a prime. A law now called quadratic reciprocity. He called it, in effect, the Golden Theorem. And the reason this matters for our story is that the same machinery, the same deep understanding of how the remainders of numbers cycle and relate to one another under a prime, is exactly what let him sort those 16 roots into the ladder of groups that collapses into square roots. The 17-sided figure was not a bolt from the blue. It was the first thing that floated to the surface of a theory so far ahead of its time that other mathematicians spent the next 100 years catching up to the book he wrote in his early 20s. He could see that 17 was constructible because he could see the entire hidden architecture of how numbers divide, an architecture nobody else had, and the polygon was just the corner of it that happened to be shaped like a picture. Everyone before him had been staring at the shape. He was the first to look underneath it at the numbers, and he could look underneath it because he had spent his teenage years quietly building the tools to do exactly that, tools the rest of the world did not yet know it needed. But let me get to what he actually saw that morning, because it is the hinge of everything, and it is beautiful in a way that is hard to overstate once it clicks. The problem, drawing a regular 17-sided figure, sounds like pure geometry. Gauss's move, the thing nobody had done, was to refuse to treat it as geometry at all. He turned it into a question about numbers, and specifically about the roots of an equation. Here is the translation. Take a circle. To place 17 evenly spaced points around it is the same, if you set the circle up on the plane the right way, as finding the 17 solutions to a single equation. The equation that asks, what are the 17 numbers that, raised to the 17th power, give you 1? The 17 17th roots of 1. One of those solutions is boring. The number 1 itself, raised to any power, is 1. That is a single point on your circle. But the other 16 are the interesting ones, spaced evenly around, and they live in the world of what are now called complex numbers. Numbers with a real part and an imaginary part, which is just the mathematician's way of giving every point on the plane an address you can do arithmetic with. And the question of whether you can construct the 17-sided figure becomes exactly the question of whether you can reach those 16 numbers using only the 5 permitted operations, the 5 we already named. Add, subtract, multiply, divide, and the square root. If those 16 roots can be built from nested square roots, the figure is constructible. If they cannot, it is not. The whole geometric problem has been converted, without loss, into a problem about the reachability of numbers. And now the arithmetic law we talked about earlier is not a side observation. It is the entire game. What Gauss then did with those 16 roots is the part that deserves to be called genius, and I do not use that word lightly. I have spent an unreasonable amount of time trying to understand exactly what he did, and I am still not sure I fully feel the bottom of it. He did not try to solve for all 16 at once, which is hopeless. Instead, he found a way to sort them. He took the 16 roots and split them into 2 groups of 8, chosen not at random but by a deep pattern in how the roots relate to one another when you multiply them. And he showed that the sum of one group of 8 and the sum of the other group of 8 are 2 numbers that together are the solutions of a single simple quadratic equation. A quadratic, the kind of equation whose solution is nothing but a square root. Then he took each group of 8 and split it again into 2 groups of 4 and showed those sums also solved a quadratic built from the numbers he had just found. Then 4 into 2 and 2, another quadratic. Then 2 into 1 and 1, a final quadratic. A ladder, 4 rungs, each rung a quadratic equation, each quadratic nothing but a square root layered on top of the square roots below it. And that is the whole thing. That is the discovery. Because every rung of that ladder is a square root, and the square root is exactly the one exotic operation the compass is allowed to perform, the entire 17-sided figure can be built. The 16 roots that had looked like a hopeless tangle turned out to be reachable by climbing a short ladder of square roots, and a compass climbs ladders of square roots for a living. The specific number at the heart of it, the exact horizontal position of one of those points on the circle, the cosine of the angle involved, can be written down explicitly. It is a single expression, and it is a monster to look at, a fraction built from a square root, inside which sits another square root, inside which sits another, and another, 4 layers of nested square roots, stacked one inside the next. But every single operation in that tower is legal. There is not one forbidden move anywhere in it. Which means it can be drawn. Which means the 17-sided figure, untouched since Euclid, impossible for 2,000 years by universal assumption, was never impossible at all. Everyone had simply failed to notice that its hardest number was hiding safely inside the world of square roots the whole time. But why 17? That is the question that turns a clever trick into a universal law. And it is the question Gauss chased next, because he was not the kind of mind that finds one door and stops. He wanted to know why the ladder existed for 17 when it did not exist for 7 or 9 or 11. What was special about the number itself? The answer is almost eerie in how clean it is. The ladder worked because of a fact about the number 16, which is 17 minus 1. When you have 17 roots and you throw away the boring one, you are left with 16 to organize, and 16 is a very particular kind of number. It is 2 multiplied by 2 multiplied by 2 multiplied by 2. 2 to the 4th power, a pure power of 2. That is the reason the roots could be split in half, and in half again, and in half again, and in half a 4th time, landing perfectly on single roots at the bottom. 4 clean halvings because 16 halves cleanly 4 times. Every halving is a quadratic. Every quadratic is a square root. The construction works precisely because the number of roots you need to organize, 16, is a power of 2, and a power of 2 can be cut in half over and over until nothing is left. Now you can feel where this is going. 7 does not work because 7 minus 1 is 6, and 6 is 2 times 3. You can halve it once, from 6 to 3, but then you are stuck with 3, which is odd, which cannot be halved into whole pieces. The ladder breaks. It hits a rung that is not a square root, that demands instead a cube root, a genuine cube root that will not simplify. And the moment you need a cube root, you have stepped outside what the compass can do. 9 fails for a related reason. 11 fails, 11 minus 1 is 10, which is 2 times 5, halve it once to 5 and you are stuck again. The whole thing comes down to a single question about each number. When you subtract 1 and look at what is left, can you keep halving it, all the way down, without ever getting stuck on an odd number bigger than 1? For 17, yes. For almost everything else, no. And Gauss, being Gauss, did not stop at a rule of thumb. He found the exact condition, and he published it 5 years later, in 1801, in the book that would reorganize the whole of number theory, the Disquisitiones Arithmeticae, which he wrote in his early 20s, and which people were still mining for insights a century later. In the final section of that book, he laid out the complete criterion for which regular polygons can be constructed, and to state it, you need to meet a very strange and very rare species of number. They are called Fermat primes, after Pierre de Fermat, the 17th century French lawyer and amateur mathematician who was better at mathematics than almost anyone doing it professionally. Fermat had been playing with numbers of a certain form. Take 2, raise it to a power that is itself a power of 2, and add 1. 2 to the first power plus 1 is 3. 2 to the second power plus 1 is 5. 2 to the fourth power plus 1 is 17. 2 to the eighth power plus 1 is 257. 2 to the 16th power plus 1 is 65,537. These are the Fermat numbers, and the first several of them are prime, meaning they cannot be divided evenly by anything except 1 and themselves. 3, 5, 17, 257, 65,537. 5 of them. 5 prime numbers of this peculiar shape. And here is Gauss's law, the machine underneath the whole 2,000-year mystery. A regular polygon can be constructed with compass and straightedge if and only if the number of its sides is a power of 2, multiplied by a set of different Fermat primes, each one used at most once. That is the entire law. Powers of 2 you get for free, because those are just the endless doublings Euclid already knew, 3 to 6 to 12, the bisecting that never stops. The real content, the thing that unlocks genuinely new shapes, is the Fermat primes. 3 is 1, that gives you the triangle. 5 is 1, that gives you the pentagon. Multiply them, 3 times 5 is 15, and you get Euclid's 15-sided figure, which is why he could build it. He had stumbled onto a product of 2 Fermat primes without knowing that was the reason. And then, for 2,000 years, the list stopped. Because the next Fermat prime, after 5, is 17, and nobody had noticed that 17 belonged to the family. Gauss noticed. That is the whole story in one sentence. He saw that 17 was the same kind of number as 3 and 5, and therefore had to obey the same rule, and therefore had to be constructible, and everyone before him had missed it, because they were looking at the geometry instead of the number. The 17-sided figure was never the point. It was the first visible piece of a hidden pattern. And once you see the pattern, you see the next shapes too. 257 sides, 65,537 sides, both Fermat primes, both therefore constructible, both perfectly drawable in principle, with nothing but compass and straightedge, shapes so close to a circle that no human eye could ever tell them apart from one, and yet, by the law, allowed. And I will come back to those 2 monsters, because somebody actually built them, and what it cost him, is one of the quietly saddest things in this entire history. But first I have to tell you about the crack in the foundation, because this is where the story turns from triumph to something colder, and it starts with the man the numbers are named after being wrong about his own numbers. Fermat, looking at his sequence 3, 5, 17, 257, 65,537, made a guess. A natural one. Every one of these he could check was prime, and he conjectured that all of them were. Every number of that form, 2 raised to a power of 2, plus 1, prime, forever, all the way up the infinite ladder. He believed it. He stated it as something he was confident of, though he admitted he could not prove it. And for about 90 years, it stood. The next number in the sequence after 65,537 is 4,294,967,297, and it is enormous, and checking whether an enormous number is prime by hand in the 17th or early 18th century was close to impossible, so Fermat's guess sat there, unchallenged, looking true. And then Leonhard Euler arrived. Euler is the other candidate, alongside Gauss, for the most formidable mathematician who ever lived, and in 1732, decades before Gauss was born, he took Fermat's 5th number, that 4 billion and change. And he did not just test it blindly. He proved something clever about what any divisor of such a number would have to look like, which cut the search down from hopeless to merely tedious, and then he found it. That gigantic number, which Fermat had assumed was prime, is not prime. It splits. It equals 641 multiplied by 6,700,417. 2 ordinary numbers, multiplied together, producing the monster. Fermat's beautiful conjecture was false at the very first number he could not personally check. The pattern he trusted broke the moment it left his reach. It is worth staying with how Euler actually did it, because it was not brute force, and the cleverness is the reason the crack in Fermat's dream is so total. That 5th Fermat number, the 4 billion and change, is far too large to check by trial in an era with no machines, no calculators, nothing but paper and a human mind. If you had simply started dividing it by 2, by 3, by 5, by every number in turn, looking for a factor, you would have been at it for the rest of your natural life and well past it. Euler did not do that. He first proved a general fact about what any divisor of a Fermat number past the second one is forced to look like. He showed that such a divisor has to be of a very specific and restricted form, that it has to be a particular kind of number related to the position of the Fermat number in the sequence. And that single insight collapsed the search from millions of hopeless candidates down to a short, manageable list of numbers that were even eligible to be factors. He walked down that short list, and very early on, he reached 641, and he divided, and it went in cleanly. The monster fell to a number you could hold in your head, found not by luck, but by first proving where it had to be hiding. That is the difference between a great mathematician and a merely tireless one. Euler did not outwork the problem. He outthought it, narrowing an infinite haystack to a few strands before he ever reached in. And there is something almost unbearably fitting about who Euler was when he did this kind of work, because he embodies, more than anyone, the sheer stubborn productivity of the mathematical mind against everything the body throws at it. He was the most prolific mathematician in history, the author of so many papers and books that a complete edition of his collected works has been in production for over a century and is still not finished. He worked through the loss of sight in one eye, and then, later in life, went nearly totally blind, and rather than stopping he seemed to accelerate, dictating page after page of mathematics to assistants, holding structures in his head that most people could not hold on paper. A blind man, calling out theorems into a room, producing a river of results that would take the rest of the world generations to absorb. He was the one who reached into Fermat's sequence and pulled out the fact that broke it. And the fact he pulled out is the one that sits under the entire question of the shapes, because every one of those Fermat numbers is a potential key. And Euler proves that the potential keys start turning out to be fakes exactly when they grow too large for anyone to easily check, which is to say essentially always, from the fifth one onward. Sit with what that means for the shapes, because this is the second foreshadow of where we are heading, and it is the moment the ground starts to tilt. The Fermat primes are the keys. Each one unlocks a genuinely new constructible polygon, and every product of them. And Fermat thought there were infinitely many keys, an endless supply marching up the number line. Euler proved that the fifth candidate is not a key at all. It is a fake. It looks like it belongs to the family, it has the right shape, but it is composite, divisible, disqualified, the run of Fermat primes, which everyone had assumed continued forever, stopped dead at the fourth one, at 65,537. After that, the next candidate is a fraud. And the one after that. And the one after that. Every single Fermat number anyone has ever managed to test beyond the fifth has turned out to be composite. Not prime. Not a key. For almost 300 years now, since Euler cracked the fifth, not one new Fermat prime has been found. The list of keys still reads 3, 5, 17, 257, 65,537, and then silence. The same 5 Gauss had. The same 5 that were already known before the United States was a country. Now you would think that Gauss, having found the law, had finished the job. He had not. And the piece he left undone is the piece this whole story turns on, and it is also the piece almost nobody who repeats the story bothers to mention, which by now you will recognise as a warning sign. When Gauss stated his law, he stated both halves of it. The first half says that if a number has the right form, a power of 2 times distinct Fermat primes, then the polygon can be built. That half he proved, completely, beautifully in the Disquisitiones. The second half is the harder and more dangerous claim. It says that those are the only numbers that work, that if a polygon has any other kind of number of sides, it is impossible, not unproven, not merely undiscovered, impossible, and this second half is the entire basis for the sentence I opened with, the claim that a 7-sided figure can never be drawn by anyone, ever. Without the second half, all you have is a list of shapes that can be built. You do not yet have a proof that anything is permanently forbidden. Gauss asserted the second half. He asserted it with total confidence, in the strongest possible language, effectively promising the reader that these were the only constructible polygons and that all others were beyond reach. But he never published a proof of it. Anywhere, and when scholars later combed through his private papers, his notebooks, that diary, looking for the missing argument, they did not find it there either. The most rigorous mathematician of his century, a man practically synonymous with the idea that you do not claim a thing until you have proven it, made the sweeping claim that 7 and 9 and 11 and almost every other polygon are impossible forever, and then simply moved on, leaving the hardest and most consequential part of the law standing on nothing but his word. Maybe he had a proof and thought it too obvious to write down. Maybe he had a sketch of one and never finished it. We do not know. What we know is that for 36 years, the claim that most polygons are impossible was technically just an assertion, a very good guess by a very great man, and the establishment, by and large, treated it as settled anyway, because Gauss had said it. And Gauss was not often wrong. The question of actually proving the impossibility, of nailing down the wall that forbids the 7-sided figure, was left hanging. And the man who eventually closed it, who supplied the missing proof that turns all my opening sentences from confident guesses into hard mathematical fact, is a name you have almost certainly never heard. His name was Pierre Wantzel. He was French, born in 1814, near Paris, into a modest family, the year before Napoleon's final defeat. And by every account, he was frighteningly good, in the specific way that certain young mathematicians are frightening. One of his teachers said of him that as a child he was already showing marks of an out-of-the-ordinary intelligence, and later described him as a mathematician of the first order. He tore through the great French engineering schools, the École Polytechnique and the School of Roads and Bridges, and he ranked first in the entrance examinations, first going in and first coming out, the kind of student the whole system is built to find and does not find often. And in 1837, when he was 23 years old, Pierre Wantzel published a paper in a French mathematics journal that did what Gauss had left undone. He proved the second half. He proved, rigorously, completely, that the numbers on Gauss's list are the only numbers that work, and that every regular polygon whose side count falls outside that list is impossible to construct. Not hard. Impossible. His argument reached down into the arithmetic we talked about, the world of reachable numbers, and showed exactly why a length that requires an unsimplifiable cube root can never be reached by square roots alone, no matter how you nest them, no matter how clever you are. He turned the wall from an assumption into a theorem. After Wantzel, the impossibility of the seven-sided figure is not a strong suspicion. It is proven, with the finality of arithmetic. And he did more than that in the same short paper, which is what makes the obscurity of his name so strange. Because the same technique, the same insight about which numbers square roots can and cannot reach, also settled two other problems that had haunted mathematics since the ancient Greeks. The first is the doubling of the cube, the old problem of constructing a cube with exactly twice the volume of a given one, which the legend says the oracle at Delos demanded of the Athenians to stop a plague. Wantzel proved it impossible because it requires reaching the cube root of 2. And the cube root of 2 is precisely the kind of number that lives outside the world of square roots. The second is even more famous, the trisection of the angle. Given any angle, can you divide it into 3 equal parts using only compass and straightedge? For over 2,000 years people had tried, and cranks are still trying today, filling the inboxes of mathematics departments with claimed solutions. Wantzel proved in that same 1837 paper that it is impossible in general, for exactly the same reason. 3 of the oldest open questions in all of mathematics, the impossible polygons, the doubled cube, the trisected angle, all closed, all proven impossible, by one 23-year-old in one paper. Using one idea, you would expect a person who did that to be a household name in mathematics, spoken of alongside the greats. He is not. And here is where the story turns genuinely dark, in the quiet institutional way that these things are dark, without a villain, without a conspiracy, just the slow machinery of who gets remembered and who does not. Wantzel's proof was correct. It was accepted in the narrow sense that the few people who read it did not find errors in it, but it was not celebrated, it was not taught. It slid into the literature and mostly vanished. For decades afterward, textbooks and lectures that discussed the impossibility of these constructions often did not mention Wantzel at all, or mentioned him only in passing. When Felix Klein, one of the most influential mathematicians of the late 19th century, wrote a famous book on exactly these problems in 1895, he laid out the impossibility proofs and did not credit Wantzel with them. The man who first proved the results was written out of the account of his own achievement, not maliciously, but through the ordinary friction of a community that had already decided, on Gauss's word, that the matter was closed and therefore did not think of the person who actually closed it as having done anything worth naming. A historian of mathematics named Jesper Lutzen wrote an entire study well over a century later, trying to answer a single question. Why was Wantzel overlooked? And his answer is not a story of injustice you can be angry at a single person for. It is worse than that, because it is structural. The results were considered important before they were proven, so once the proof arrived it felt like a formality, a confirmation of something everyone already believed. The proof was seen as filling in a detail, not as a discovery. precisely because Gauss had already asserted the conclusion with such authority that the conclusion felt like common knowledge. There is a pattern here, and it is worth naming directly. First, the thing is impossible and mysterious. Then a great man asserts the answer, and everyone believes him. Then a younger, lesser-known man actually proves it, and because everyone already believed the answer, the proof is treated as trivial. The one thing the proof is never allowed to be is important. The realer the work, the more invisible the worker. You can watch the erasure happen even in the name of the result. Today, when the theorem is named at all, it is usually called the Gauss-Wantzel theorem, which sounds fair, two names, shared credit. But look at what each name is doing. Gauss supplied the easier half, the constructions, and asserted the harder half without proof. Wantzel supplied the harder half, the actual proof of impossibility, the thing that makes the whole result a theorem rather than a conjecture. And yet the name puts Gauss first, as it always will, because Gauss is Gauss, and Wantzel comes second, a kind of footnote to the man who did not finish the job. Almost everyone who casually knows this material knows it as Gauss's result. The 17-sided figure is Gauss's triumph. The impossibility of the 7-sided figure is, vaguely, also credited to Gauss in the popular telling, and Wantzel, who actually proved that impossibility, evaporates. The proof got absorbed into the reputation of the man who guessed the answer, and the man who proved it kept almost none of the credit for the proving. That is how the machinery works. It is not that anyone decided to rob him, it is that a proof of something everyone already believes feels like tidying up, and tidying up does not get your name remembered, even when the tidying up is the single hardest and most important step, the one that converts a brilliant guess into certain knowledge. Gauss opened the possibility. Wantzel closed the impossibility. And closing the impossibility is, in a strict sense, the greater and more final act, because a possibility can be confirmed by a single example, while an impossibility must be proven against every possible attempt at once, forever. He did the harder thing. He got the smaller share of the name. And Pierre Wantzel did not have long to be overlooked in. He worked himself to death. This is not a figure of speech. The people who knew him described a man who slept little, who ate irregularly, who drove himself with a kind of reckless intensity, and who leaned on coffee and, by one contemporary account, opium, to keep going through nights of work. A colleague who wrote his obituary described him as ordinarily working evenings, not lying down until late, then reading, and taking only a few hours of restless sleep. He burned the candle from both ends and the middle. And he died in 1848 at the age of 33. The man who defined, more precisely than anyone before him, the exact boundary of what is possible with these tools, the man who drew the permanent line between the shapes that can exist and the shapes that are forbidden, ran out of his own life at 33. His single most important result already sliding into an obscurity it would not climb out of for 100 years. He proved what could not be done, and what he could not do was stop. Now we can say exactly what is forbidden, and I want to make it concrete, because it is one thing to talk about impossibility in the abstract, and another to hold the specific shapes in your hand and feel that they cannot be drawn. Start with the 7-sided figure, the heptagon, the shape I opened with. 7 is a prime number, but it is not a Fermat prime. 7 minus 1 is 6, and 6 is 2 times 3, and that stubborn factor of 3, which is odd and will not go away, is the whole problem. When you turn the 7-sided figure into its equation and try to build the ladder of square roots, the ladder cannot be built. At the crucial rung, it demands a cube root that will not simplify into square roots by any trick. And the cube root is a door the compass cannot open. Wantzel's proof makes this airtight. There is no clever construction waiting to be discovered. There is no sequence of arcs and lines, however long, however ingenious, that produces a perfect regular heptagon. The impossibility is not a gap in our knowledge, it is a feature of the number 7, and it will be just as impossible for every mathematician who ever lives, on every world, until the end of time. Then the 9-sided figure, and this one is my favourite, because it is a disguise. 9, you might think, should be fine, 3 is a Fermat prime, 3 gives you the triangle, and 9 is just 3 times 3. But look again at the law. It requires distinct Fermat primes. Each one used at most once. 9 is 3 squared, the same Fermat prime used twice, and that repetition is forbidden. 2 3s are 1 too many. And so the 9-sided figure is impossible. But here is the disguise. The thing that made me sit up when I first understood it. Constructing a regular 9-sided figure is exactly the same problem as trisecting a 60-degree angle. The 9-sided figure is what you would get if you could cut the angles of an equilateral triangle into 3 equal pieces each. And so the impossibility of the 9-sided figure and the impossibility of trisecting the angle are not 2 separate facts. They are the same fact, wearing 2 different costumes. The ancient Greek problem that people are still, today, mailing crank solutions to universities about, and this seemingly innocent 9-sided polygon, are secretly the identical wall. Wantzel knocked them both down with the same swing. And then, you start counting the dead, and the scale of the forbidden becomes clear. 11, impossible. 13, impossible. 14, which is 2 times 7, impossible because it inherits the impossibility of 7. 18, which is 2 times 9, impossible, inheriting the impossibility of 9. 19, 21, 22, 23, 25, all impossible. If you make a list of the number of sides and you mark which regular polygons can be drawn, the marks are sparse. 3, 4, 5, 6, 8, 10, 12, 15, 16, 17, 20, 24, and then a widening desert with only occasional oases. The overwhelming majority of regular polygons, if you could line them all up, are on the forbidden side of Wantzel's wall. Drawability is the rare exception. Impossibility is the rule. The pentagon on your notebook, the hexagon in a honeycomb, the octagon on a stop sign, these are the lucky few. Almost every other regular shape you could name is a ghost. Nameable, definable, perfectly precise as an idea, and permanently unbuildable with the tools that built all the others. There is something worth noticing about exactly where the wall falls, because it does not fall in some distant exotic region. It falls right in the middle of the shapes you see every day, cutting between neighbours that look almost identical. 6 sides, the hexagon, is on the permitted side, and it is permitted for a humble reason. 6 is 2 times 3, and 3 is the triangle, and doubling is free. So the hexagon is just a triangle that has been bisected around, which is why you can draw it so easily, and why nature reaches for it constantly. The cells of a honeycomb, the cracks in cooling basalt, the packing of bubbles, all hexagonal, because 6 around a point tiles the plane perfectly, and the shape is in a deep sense, easy, sitting comfortably inside the reachable world. And then you take one step. 7, the very next number. And you fall off the edge of the possible entirely. 6 is constructible and ordinary and everywhere. 7 is forbidden, forever, provably, by the cube root wall. The line between the permitted and the impossible does not run somewhere far away where you would never notice it. It runs directly between the hexagon in the honeycomb and the heptagon that cannot exist, 2 shapes that differ by a single side, one of them the most natural shape in the physical world, and the other one of the most impossible. The same thing happens all along the number line. 8, the octagon on every stop sign, is fine, because 8 is a doubling of the square, 2 doublings really. 4 to 8, all free. 9, one step further, is forbidden, the trisected angle in disguise. 10 is fine, a doubled pentagon. 11 forbidden, 12 is fine, a doubled hexagon. 13 forbidden, the reachable and the forbidden are braided together tightly, alternating, neighbouring, and there is no way to tell which is which just by looking at the shape or counting how close its sides are. You have to go underneath, to the number, and ask the one question that decides everything, whether the number, stripped down, is built only from the doublings and the 5 keys. The stop sign is allowed. A regular shape with one more side than the stop sign is not, and never will be, and you would never guess it from looking. The wall is invisible and it is everywhere, running quietly between the shapes we use without thinking and the shapes that were never permitted to be. But that is not the strangest part of the catalogue. The strangest part is what happens at the top, with the 2 monsters Gauss's law promises are constructible. The 250 7-sided figure and the 65,537-sided figure, both Fermat primes, both by the law buildable with compass and straightedge, and people actually tried to build them, which is where the human cost sneaks back into a story that had briefly become abstract. The 250 7-sided figure was worked out first. A mathematician named Friedrich Julius Richelot published a construction for it in 1832 in one of the major mathematical journals of the day, and the write-up ran to something on the order of 190 pages. Almost 200 pages of dense construction to pin down a single shape. A shape which, if you drew it, would be visually indistinguishable from a circle. 257 sides packed around a circle are so close together that no eye, no ordinary measurement, could tell you it was not simply round. And a serious mathematician spent the effort to produce 200 pages proving you could draw the thing that looks exactly like the thing you can already draw trivially. That is either the purest expression of mathematical devotion or a small tragedy, and honestly I cannot decide which, and I think the inability to decide is the correct response. And then there is the last one, the 65,537-sided figure, the largest Fermat prime anybody knows, and therefore the largest genuinely new drawable polygon the law permits from a single key. A German schoolteacher named Johann Hermes decided he would construct it, not sketch it, not prove it constructible in the abstract, which Gauss's law had already guaranteed, but actually carry out the full explicit construction. Every step, the complete recipe. And it took him 10 years. 10 years of one human life spent producing the step-by-step construction of a 65,537-sided regular polygon. The finished work filled a manuscript of over 200 pages. He completed it in 1894, and the manuscript, this decade of a man's labour, was deposited at the University of Göttingen, the same university where Gauss had seen the 17-sided figure 100 years earlier, and it is, by most accounts, still there, sitting in a trunk, a physical object you could in principle go and look at. Think about the shape he was drawing. 65,537 sides. If you constructed it at any reasonable size and looked at it, you would see a circle. There is no possible way for a human eye to distinguish a 65,537-sided regular polygon from a perfect circle. The corners are too many and too shallow, and so Hermes spent 10 years, a real decade of a real life, producing an exact construction of something that is, to every sense you possess, simply a circle. He did it because the law said it could be done, and because doing it, actually walking every step of the path Gauss had proven existed, was a mountain that was there. And I find I cannot quite laugh at it, even though there is something absurd in it, because it is also the most literal possible demonstration of the gap this whole story lives in. The gap between what is provably possible and what any of us can actually see or touch or use. Gauss proved the door existed. Hermes spent 10 years walking through it, and on the other side was a shape indistinguishable from the circle he started with. There is a detail here I have to be honest about, because this story rewards honesty and punishes the polished version, and it fits the pattern too well to leave out. Some later mathematicians, looking at Hermes's enormous manuscript, have quietly wondered whether it is even correct. The mathematician John Conway, one of the sharpest and most playful minds of the 20th century, is reported to have examined it and expressed doubt about whether the construction actually holds up, whether 10 years of work produced a valid result or a flawed one buried in its own vastness, and nobody, as far as I can tell, has fully checked it, because checking 200 pages of explicit construction for a 65,537-sided figure is itself a monstrous undertaking that no one has been sufficiently motivated to complete, and we do not entirely know. A decade of a man's life, sealed in a trunk at Göttingen, possibly a triumph, possibly flawed, and the community's honest position is a shrug. The realer the work, the more invisible the worker. It keeps happening. It happened to Wantzel with a proof that was right, and it may be happening to Hermes with a construction that might be wrong, and in both cases the lesson is the same. Doing the actual work, all the way down to the last step, is a thankless place to stand. I want to slow down and actually look at one of the winners, because so far the drawable shapes have just been names on a list, and there is a reason the lucky few are lucky, and it is genuinely lovely once you see it. Take the pentagon, the 5-sided figure, the simplest interesting shape on the permitted list, the one Euclid already had. 5 is a Fermat prime, which is why it works, but what does that mean when you actually build it? It means that hiding inside the pentagon is the golden ratio, that famous number a little larger than 1.5 that shows up in art and architecture and the spiral of a shell. The ratio you get when a line is divided so that the whole is to the larger part, as the larger part is to the smaller. The diagonal of a regular pentagon, the line from one corner across to a non-adjacent corner, is exactly the golden ratio times the length of its side. And the golden ratio is a number you can build with square roots. It is 1 plus the square root of 5, all divided by 2. Nothing but a square root and some arithmetic, which is precisely why the pentagon is constructible. The number at its heart lives safely inside the world the compass can reach. When you draw a regular pentagon with a compass and straightedge, what you are really doing underneath the arcs is constructing the golden ratio and hanging a shape on it. The beauty people have chased in that ratio for centuries, and the drawability of the 5-sided figure are the same fact. The shape is buildable because its hidden number is gentle enough to be reached. That is what a winning number looks like. A number that reduces, however elaborately, to square roots. And the 17-sided figure is a winner for the same reason, except its hidden number is far less gentle. Where the pentagon needs a single square root, the 17-sided figure needs that tower of nested square roots 4 layers deep, square roots inside square roots inside square roots, the monster expression Gauss wrote down. But every layer is still a square root, so the tower still stands inside the compass's reach, and the shape is still buildable, just with a great deal more work. And that work, when someone finally did lay it out as an actual construction, is strangely humble to look at. There is a clean modern version, the one Herbert Richmond published in 1893, and there is an elegant way to organise it using what are called Carlyle circles, named after Thomas Carlyle, the essayist, who as a young man had a mathematical streak. And when you follow the steps, it is just circles and lines. Draw a circle, mark the centre, drop a perpendicular, find a midpoint, draw an arc from here to there, bisect an angle. A few dozen careful moves with the 2 ancient tools, and slowly, out of nothing but intersections, 17 evenly spaced points appear around the circle, and you connect them, and there it is. The shape that took 2,000 years to become possible, drawn with the exact same compass, and Straightedge a Greek geometer would have recognised on sight. No new tool was ever needed. The tools had always been capable of it. The missing piece was never the instrument. It was the understanding of what the instrument was secretly doing to numbers. and that understanding is the thing Gauss supplied at 18. But all of this, the possible shapes and the impossible ones, the monsters at the top and the ghosts in the desert, still leaves the biggest question of the whole story untouched. And it is the question I planted at the very beginning, and it is time to let it fully open, because it is the one that has no answer. And the fact that it has no answer is the most unsettling thing here. The keys are the Fermat primes. 3, 5, 17, 257, 65,537. 5 of them. And every genuinely new drawable regular polygon with an odd number of sides comes from these keys and their products. Multiply them together in all the different combinations, and you get the complete set of odd-sided regular polygons that can ever be drawn. If you count them, taking each of the 5 keys as either used or not used, you get 31 different odd-sided constructible polygons. 31. That is not a figure of speech or an approximation. If the 5 known Fermat primes are the only Fermat primes that exist, then there are exactly 31 odd-sided regular polygons in the entire infinite universe of shapes that a compass and straightedge can construct, and the largest of them has 4,294,967,295 sides, and it is drawable, and beyond it. Among the odd numbers, there is nothing, ever if that word is carrying the entire weight of the story now, and here is where it gets genuinely uncomfortable, because the if has been open for almost 300 years and shows every sign of staying open. Are there more Fermat primes? Is there a 6th key somewhere out there on the number line? A 6th number of that special form? 2 raised to a power of 2 plus 1 that turns out to be prime and unlocks a new shape? Nobody knows. That is the honest answer, and it is a strange thing to be able to say about a question this old and this simple to state. We do not know if there is a 6th Fermat prime. And it is not for lack of looking. People have hunted these numbers for centuries. And as computers arrived, the hunt turned industrial, and the results have all pointed in one direction, and that direction is silence. Every Fermat number that anyone has been able to test, past the 5th one, has turned out to be composite, not prime. Euler killed the 5th in 1732. The 6th, 7th, 8th, all fell to later mathematicians, all composite. And the numbers get large in a way that is genuinely hard to hold in the mind, because each Fermat number is roughly the square of the one before it. The exponents do not grow. They double, and then the number is 2 raised to that doubled exponent. By the time you are a little way up the sequence, you are dealing with numbers whose digit counts are themselves enormous numbers. And still they get tested, at least partially, and still they come back composite. Mathematicians have now shown that every Fermat number from the 5th all the way up to at least the 32nd is composite. Every single one, not a prime among them. And it goes further than that, into a scale that stops being about numbers and starts being about the limits of physical reality. In recent years, using vast computer searches, people have found factors of Fermat numbers so large that the Fermat number itself could never be written down. There is a Fermat number, discovered to be composite in the last few years, whose position in the sequence is over 18 million. To even write out how many digits that number has would take a string of digits longer than anything you have any intuition for. It is a number so large that if you tried to print it, using every atom in the observable universe as a single digit, you would run out of universe long before you ran out of number. And a mathematician, using a distributed computer search, found a factor of it, proved it composite, proved that this unimaginable colossus is not prime, and therefore not a key, and therefore does not unlock a new shape. The search for the 6th Fermat prime has pushed into regions so far beyond human scale that the objects being tested cannot be represented in the physical universe. And the answer, every single time, comes back the same. Composite, No key here. Keep looking. And here is the part that tips the whole thing from an open question into something that feels almost like a verdict, though it is not a proof, and the difference between those two things is exactly the abyss this story lives over. There is a heuristic argument, a probabilistic estimate based on how often numbers of a given size tend to be prime. That predicts how many Fermat primes we should expect to find beyond the ones we know. And the answer that argument gives is, essentially, none. The expected number of additional Fermat primes, according to this reasoning, is a fraction so small it rounds to 0 for any practical purpose, a number with many zeros after the decimal point before you reach a non-zero digit. The mathematics of probability is quietly telling us that the 5 keys we have are, in all likelihood, the only 5 keys there are, that the list is not just currently frozen, but frozen forever. That 65,537 is very probably the last key that will ever be found, because it was very probably the last one that ever existed to be found. But, and this is the crucial but, the one that keeps the question open, and will keep it open possibly for as long as mathematics is practiced, that is a heuristic. It is an educated expectation, not a theorem. Nobody has proven that there are only finitely many Fermat primes. Nobody has proven there are infinitely many. Both possibilities remain, formally, on the table. It is entirely possible that there are only 5 Fermat primes in all of infinity, and it is entirely possible that somewhere out there, at a scale that dwarfs everything we have searched, a 6th one waits, and a 7th, an infinite scattering of them growing ever rarer, but never stopping. We cannot rule it out. We cannot rule it in. The question sits exactly where it sat when Euler broke the 5th number in 1732, refusing to close. And that means the question I opened with genuinely has no answer. How many regular shapes can the oldest tools in mathematics draw? If the list of keys is complete, then the full and final catalogue of constructible regular polygons is fixed, known, and closed. And it was essentially complete the moment Gauss recognized that 17 was a Fermat prime. If the list of keys is not complete, then somewhere in the unreachable distances of the number line there are new shapes, drawable in principle, that no one has ever named, waiting behind keys we have not found and may never find. And we do not know which of these two universes we live in. We have lived without knowing for 3 centuries. We may live without knowing forever. The most likely answer, the answer probability whispers, is that the catalogue is closed, that a poor labourer's son in Brunswick very nearly wrote the last line of a book that Euclid started 2,000 years before him. But likely is not certain, and in mathematics only certain counts. And certainty here has never come, and may never come. I want to slow down and make sure the shape of this lands, because it is easy to let it slide past as just another unsolved problem, and it is much more than that. Most open problems in mathematics are questions about things we cannot yet compute or prove. This one is different in a way that gets under the skin. This is a question about whether a catalogue of shapes as concrete and ancient as the triangle and the pentagon, is finished, whether the book is closed. And the reason we cannot answer it is not that the shapes are complicated. The shapes are trivial to describe. The reason we cannot answer it is that it depends on the deepest and most stubborn kind of fact there is. The fact about which numbers in the infinite sequence of the Fermat numbers happen to be prime. And primality, the simple question of whether a number has any divisors other than 1 and itself, is one of the oldest and hardest veins in all of mathematics. The constructibility of shapes, the most visual and intuitive thing imaginable, turns out to be chained to the primality of specific gigantic numbers, the most austere and unforgiving thing imaginable. The picture depends on the number, and the number will not tell us what it is, and there is a deeper layer underneath even that, because the question of why square roots are allowed and cube roots are not why the compass can reach some numbers and not others, opened into one of the most important ideas in all of mathematics, and it came from another young man who died even younger than Wantzel, in circumstances even more senseless, and whose work was ignored even more completely. If you are starting to sense a pattern in who pays the price for these truths, you are right too, and this is the sharpest example of it. His name was Évariste Galois, French again, born in 1811, 3 years before Wantzel, and he was not merely talented, he was one of those figures who seemed to arrive from some other place, thinking in a language the mathematics of his time did not yet have words for. He failed the entrance exam to the École Polytechnique twice, partly because his ideas were too far ahead of the examiners to follow, partly because he could not or would not show the tedious intermediate steps that were obvious to him. He was politically radical in a turbulent France, was arrested, spent time in prison, and in 1832, at the age of 20, he was drawn into a duel, the exact reasons for which are still argued about. Something involving a woman and possibly a political setup. The night before the duel, believing he might die, he sat up writing, frantically setting down his mathematical ideas in a long letter to a friend, scrawling in the margins, at one point writing that he had no time. No time. The next morning he was shot in the abdomen and left on the ground. He died the following day, 20 years old. And the ideas he scrawled that night turned out to be the key to everything we have been talking about, and to vastly more. Galois had found the deep reason why some equations can be solved with roots and others cannot. He had discovered that hidden inside every equation is a kind of structure, a set of symmetries, a group, and that the solvability of the equation, whether you can crack it open with square roots and cube roots and higher roots, is written into the architecture of that hidden structure. This is now called Galois theory, and it is one of the pillars of modern mathematics, and it is the framework that makes the constructibility of polygons not a mysterious special fact, but a clean consequence of a general principle. The reason the compass is limited to square roots is, in the language Galois invented, a statement about the sizes of these hidden symmetry structures being powers of 2. Every regular polygon, every construction, every impossibility we have discussed sits inside Galois' framework as a small and almost obvious example. He gave us the machine that explains the machine, and when he died at 20, in a field outside Paris, his work was not celebrated. It was not understood. The papers he had submitted to the French Academy had been lost or set aside, or rejected as incomprehensible by some of the most eminent mathematicians of the age, men who could not see what they were holding. His night before letter, with its desperate no time in the margin, was published by a friend, but it took more than a decade after his death before the mathematical world began to grasp what he had done, before Galois theory became Galois theory rather than the unreadable scribblings of a dead radical. He is now considered one of the most important mathematicians who ever lived. He did not live to see a single page of that recognition. He was a teenager, and then he was briefly a young man, and then he was a body in a field, and the machinery that would eventually explain the impossibility of the seven-sided figure and the trisected angle and the doubled cube was already complete in his head and nearly lost with his blood. Count them now. Gauss, the exception, who lived long and was honoured and became a legend, though even he left the hardest half of his own law unproven, and it fell to others to finish. Wantzel, who proved that hardest half, dead at 33, worked into the ground, forgotten for a century. Galois, who found the framework beneath all of it, dead at 20 in a duel, ignored until long after he was gone. Hermes, who spent 10 years drawing a shape that looks like a circle and may have gotten it wrong, sealed in a trunk. There is a pattern in this story, and it has nothing to do with the quality of the mathematics. The mathematics is eternal and perfect. It is the people who are fragile, and it is specifically the people who do the hardest, realist, most finishing work who tend to vanish, while the conclusions they proved float free of them and become common knowledge that everyone believes and no one attributes. The truths survive. The truth tellers over and over do not. I said at the start that the deepest thing in this story got lost, the same way the number 19 got lost, sanded down and made comfortable until the uncomfortable core disappeared. And now I can tell you what I meant. The comfortable version of this story is the one you have probably heard. A teenage genius solves an ancient problem in a single morning and goes on to greatness. It is a triumph. It is inspiring. It fits on a plaque. And every hard edge has been filed off it. The edge where he was 18 and not 19. The edge where he never actually drew the shape. The edge where the man who proved the impossibilities died exhausted and uncredited. The edge where the framework came from a boy shot dead at 20. And the deepest edge of all, the one that almost never survives the retelling, which is that the discovery was not really the opening of a door, it was the finding of a wall. Gauss did not show us how much we could draw. He and Wantzel and Galois together showed us how little. They mapped the exact and permanent boundary of what these tools can do, and the map is mostly forbidden territory, and the small permitted region may already be completely known, closed, and finished. The triumphant version tells you a genius expanded the possible. The true version is colder. The genius found the edge of the possible, and the edge turned out to be very close, and almost everything lies beyond it, forever out of reach, not because we are not clever enough, but because the numbers themselves refuse. Because that is what the compass and straightedge really are, underneath the geometry, and this is the thing I keep circling back to in my own head. They are a physical question put to the universe of numbers. You hand the tools a single length, and you ask, what else can I reach from here? And the tools answer, honestly and without mercy. You can reach whatever you can build from square roots, and nothing else. And the numbers that live outside the reach of square roots, which is almost all of them, the cube roots and the fifth roots, and the vast wild majority of numbers that cannot be captured by any finite tower of square roots at all, those numbers are simply unreachable. Not hard to reach. Unreachable, they exist, they are as real as any number, they sit there on the line perfectly well defined, and no compass, no straightedge, no combination of the two wielded for 1 billion years will ever touch them. The shapes we cannot draw are just the visible shadow of this deeper fact. The forbidden heptagon is not really about 7 sides. It is about a single number buried in its construction that lives in the unreachable dark, and the 7-sided figure is impossible because that one number can never be reached, and that one number can never be reached because of what the number is, and there is no appeal, no workaround, no clever trick above the law of what square roots can and cannot build. And the list of keys, the Fermat primes, sits at the very centre of this, holding the door. 5 keys found, none in 300 years. Probably none remaining anywhere in the infinite line, but not provably none. That is where we have stood since 1732. That is where we still stand tonight. The catalogue of drawable shapes hanging on a question about the primality of numbers so large they cannot be written in the physical universe, a question that has resisted every mind that has ever attacked it, and shows no sign of yielding, and may never yield. Let me put you inside the impossibility, because I think it only really lands when you feel your own hand hit the wall, rather than being told the wall is there. Sit down with a compass and a straightedge and a blank sheet, and decide you are going to draw a perfect regular 7-sided figure. You know it has 7 equal sides and 7 equal angles. You start, reasonably, by drawing a circle, because the vertices of a regular polygon all sit on a circle, and if you can mark 7 evenly spaced points around it, you are done. The real task, then, is to divide the circle into 7 equal arcs. You need to step around the circle in 7 identical jumps and land exactly back where you started. Each jump is an angle, and 7 of them make a full turn, so each one is a full turn divided by 7. And to mark that angle with your tools, you need to construct a specific length. The horizontal distance corresponding to that angle the cosine of 1/7 of the way around. That length is a specific number, and whether you can construct the figure comes down entirely to whether you can build that one number out of your starting unit using the 5 permitted operations. Now you try. And at first it goes well, because the number that governs the 7-sided figure is a solution to a particular equation, and that equation, it turns out, can be simplified down to a cubic, an equation involving a number multiplied by itself 3 times. And here is the exact moment the wall arrives. A cubic equation, in general, cannot be solved with square roots. Its solution, when it will not factor into anything simpler, requires a cube root, a number that must be multiplied by itself 3 times to get a target. And the cube root is the one thing the compass cannot do. The compass does square roots. It intersects circles and lines and hands you square roots all day long. It has no operation anywhere in its repertoire that produces a genuine cube root, and this particular cubic, the one that governs the 7-sided figure, is what mathematicians call irreducible over the rationals, meaning it stubbornly refuses to break apart into simpler pieces that square roots could handle. The cube root it demands is real, and it is necessary, and it is forever outside your reach. That is the whole wall, and notice what kind of wall it is. It is not that the construction is long, it is not that it is delicate, it is that at one specific step, the mathematics asks you to perform an operation your tools do not possess and cannot be made to possess, no matter how you combine them. It is like being asked to reach a note that is simply not on your instrument. You can play faster, you can play more cleverly. You can practice for 1,000 years, and the note is still not there. The 7-sided figure lives one operation beyond the edge of the compass, and that one operation is a cliff with no bottom. And once you understand the shape of that wall, you realize the 7-sided figure was never alone against it. It stands with 3 of the most famous problems in the entire history of mathematics, the 3 great construction problems of antiquity, all of which turn out to be the same wall seen from different angles. 2 of them Wantzel knocked down in his 1837 paper, and we have met them already. The doubling of the cube, which asks for the cube root of 2, and is refused for exactly the reason the 7-sided figure is refused, a cube root the compass cannot reach, and the trisection of a general angle, which is the 9-sided figure in disguise, and fails the same way. 2 ancient walls, both revealed to be the cube root wall wearing costumes. But the 4th ancient problem is the largest of them all, and it is worse than a cube root wall. It is the one that gave us a phrase that is still in the language, that people say without knowing where it came from: squaring the circle. And the reason it is worse is that the circle does not fail because of a cube root. The circle fails because of a number so far outside the reach of these tools that it is outside the reach of nearly all of mathematics, a number that Gauss and Wantzel and even Galois did not have the tools to fully condemn. And that took until almost the end of the 19th century to finally sentence. Squaring the circle is an old dream. Given a circle, construct, with compass and straightedge, a square with exactly the same area. It sounds so reasonable. A circle has an area. A square has an area. Surely you can find the square that matches. People chased it for more than 2,000 years, longer than any of the others, longer than almost any problem in the history of thought. The ancient Greeks tried. Medieval scholars tried. It became a symbol of futile obsession so well known that Dante put circle squares in his poetry as an image of a mind straining at something just past its grasp. And the reason it is impossible reaches deeper than everything else we have discussed, because it depends on the nature of a single number, the most famous number in mathematics, the ratio of a circle's circumference to its diameter. Pi, to square the circle, you would need to construct a length involving pi. And so the whole ancient problem reduces, once again, to a question about the reachability of a single number. Can you build pi, or the square root of pi, from your starting unit using the 5 permitted operations? And to answer that, you first have to understand what kind of number pi even is, and this is where the story climbs past square roots and cube roots into a different category of the forbidden altogether. Remember that the constructible numbers, the reachable ones, are the ones you can build from square roots. Those numbers are all what mathematicians call algebraic. An algebraic number is one that is a solution to some polynomial equation with ordinary whole number coefficients. The square root of 2 is algebraic. It solves the equation that asks for a number whose square is 2. Even the cube root of 2, unreachable by the compass, is still algebraic. It just needs an operation the compass lacks. Every number the compass can reach is algebraic, though not every algebraic number can be reached. But there is a second, stranger kind of number, numbers that are not the solution to any polynomial equation with whole number coefficients at all. No equation of that kind, ever, captures them. These are called transcendental, and they were long suspected to exist but not proven to until the middle of the 19th century. A transcendental number is not just beyond the compass, it is beyond all of algebra. It cannot be pinned down by any finite equation of the ordinary kind. It transcends the whole machinery. And in 1882, a German mathematician named Ferdinand von Lindemann proved that pi is transcendental, not merely irrational, which had been known for a century. Transcendental, pi is not the solution to any polynomial equation with whole number coefficients. It lives entirely outside the algebraic world, and therefore infinitely far outside the tiny constructible corner of that world. And with that single proof, the 2,000-year-old dream of squaring the circle died, permanently and completely. Because if pi cannot be reached by any polynomial at all, it certainly cannot be reached by the compass, which can only reach a thin sliver of the algebraic numbers. The circle cannot be squared. Not because the construction is hard, because pi is transcendental, and a transcendental number is a place these tools can never go, and no tools built on this kind of arithmetic ever could. Lindemann did to the circle what Wantzel did to the polygons, drove the final nail, converted an ancient assumption into a proven and permanent impossibility, and closed the last of the 4 great problems of antiquity. And here is the human part, the part that connects all of this back to you, sitting there, hearing it, because it is the part that reveals what happens when a proven impossibility is never actually told to the people who need to hear it. You would think that once these things were proven, once Wantzel and Lindemann had closed the books, people would stop. They did not stop. They have never stopped. To this day, mathematics departments and journals receive a steady trickle of manuscripts from people, often intelligent, often sincere, often having spent years of their lives on it, claiming to have trisected the angle, or squared the circle, or found a construction for one of the forbidden shapes. There is a whole quiet genre of these. A mathematician named Underwood Dudley wrote entire books cataloguing them, the trisectors and the circle squarers, people who have devoted enormous stretches of their one life to a task that was proven impossible before they were born. And Dudley wrote about them not with mockery, but with a kind of sorrow, because the striking thing about these people is not that they are foolish, it is that they were never told. The impossibility, one of the most beautiful and definitive results in all of mathematics, sits locked inside the professional literature, and it never reached them. They grew up being taught that a compass and straightedge can draw anything with enough patience, the same intuition you started this video with, and nobody ever handed them the proof that says otherwise, and so they poured their years into a wall they did not know was a wall, mailing their solutions to universities that quietly set them aside, the way the Academy set aside Galois, the way everyone set aside Wantzel. The proof exists. It has existed for well over a century, and it still, somehow, does not reach the people spending their lives crashing into the thing it describes. That is the invisible scandal underneath this whole story, and it is not a scandal of suppression exactly, not a conspiracy, just something quieter and in a way sadder. The most important thing to understand about these tools, the fact of what they cannot do. The permanent boundary of the possible is knowledge that was hard won by people who mostly died young and uncredited, and it is knowledge that, having been won, was filed away and never handed out. You were taught the shapes you can draw: the triangle, the square, the pentagon, the hexagon. You were shown how in school with a compass, and it felt like the beginning of an endless list. Nobody sat you down and told you that the list was almost entirely finite, that the shapes you were drawing were the rare exceptions, that 7 and 9 and 11 and almost everything else were walled off forever by a law of arithmetic proven by a Frenchman who worked himself to death at 33. That half of the story, the boundary, the wall, the map of the forbidden, is the half that never makes it onto the plaque, and it is the more important half. Because knowing what you can do is useful, but knowing the exact and permanent edge of what can ever be done, that is a rarer and colder and more valuable kind of knowledge, and almost nobody is ever given it. I want to widen the lens now, all the way out, because there is something about the word impossible that we use loosely in ordinary life and that means something entirely different here, and the difference is the whole reason this story has the weight it does. In everyday speech, impossible almost always means very hard, or not yet, or beyond current technology. It was impossible to fly until it was not. It was impossible to reach the moon until it was not. We are trained by our own history to hear impossible as a temporary verdict, a challenge, a thing that clever people will eventually overturn. And in almost every domain of human effort, that instinct is correct. The impossible of one century is the routine of the next, but mathematics is the one place where impossible can mean something absolute, where it is not a statement about our cleverness or our tools or our era, but a proven property of the thing itself, as permanent as the fact that 2 and 2 make 4. When Wantzel proved the 7-sided figure impossible, he did not mean that no one had managed it yet. He meant that it sits, provably, forever, outside the reach of these tools, and that this will be as true 1 billion years from now, for any mind anywhere, as it is tonight. That kind of impossible does not get overturned. It does not yield to better technology or a smarter generation. It is closed in a way that almost nothing else in human experience is ever closed. And we, who live inside the everyday meaning of the word, have almost no intuition for that. We keep expecting the wall to come down, because every other wall eventually did. This one will not. This one is made of the same stuff as arithmetic, and arithmetic does not negotiate. And when you look at exactly how much of the world of numbers these tools can reach, the picture becomes vertiginous. Think of all the numbers on the line, every possible length, the whole continuous sweep of them. The numbers you can construct with a compass and straightedge are a subset of that sweep, and it is worth asking how big a subset. The answer is almost incomprehensibly small. The constructible numbers are countable, meaning you could in principle list them one after another in an endless sequence. First, second, third, and so on. But the full set of numbers on the line is not countable. It is a larger kind of infinity entirely, an infinity so much bigger that if you could somehow throw a dart at the number line and hit a truly random point, the probability that you would land on a constructible number is exactly 0. Not small. 0. The reachable numbers are so sparse against the background of all numbers that they take up no width at all. They are a scattering of isolated points in an ocean that is almost entirely unreachable. Almost every number that exists is not constructible, is not even algebraic, is one of the transcendental multitude that no equation and no compass will ever touch. Take that in for a moment, because it inverts the entire feeling of the story. We started with a triumph, a young genius adding a new shape to the ancient list, and it felt like an expansion, a door opening, the possible growing larger, and it was, locally, a real and beautiful expansion. But when you pull all the way back, what the whole enterprise reveals is the opposite. It reveals how tiny the reachable region is. The compass and straightedge these tools that feel like they could draw anything reach a set of numbers so thin it has no size at all, and they miss, permanently, almost everything. The constructible shapes, the constructible numbers, the whole domain of what these ancient tools can build is a measure zero island in an uncountable sea. And Gauss, and Wantzel, and Galois, and Lindemann, between them, did not just find the island. They mapped its coastline exactly. They told us precisely where the land ends and the water begins, and the water is nearly all of it, and it goes on forever, and none of it will ever be reached. And the island itself, the little scrap of reachable land, the part that includes the drawable regular polygons, might already be completely surveyed. That is the thread I have been pulling this whole time, and it does not let go. Among the odd-sided regular polygons, the reachable ones come from the Fermat prime keys, and there are 5 known keys, and there have been 5 known keys since before there was a United States, and the mathematics of probability quietly insists there are almost certainly no more, and yet no one has been able to prove there are no more, and no one has found a 6th, despite searching into numbers larger than the physical universe could contain. The map of the reachable island may be finished. The catalogue of drawable regular shapes may be closed and complete, and final. 30 one-odd-sided shapes and their doublings and nothing else. Forever, or there may be, somewhere out in the unreachable distances, one more key, or a scattering of them, waiting behind a question about primality that has defeated every mind for 300 years. We stand at the edge of a finished map that we cannot prove is finished, staring into a distance we cannot search, holding 5 keys and wondering if they are all the keys there are, and nobody can tell us. Nobody has ever been able to tell us. The most likely answer is that a labourer's son, one spring morning before he got out of bed, came within a hair of writing the final entry in a book 2,000 years old and closing it. But likely is not proven, and the book lies there, maybe finished, maybe not, and no living person knows which. I want to come back at the end to the man who started it, because there is a detail about how Gauss wanted to be remembered that I have been saving, and it turns out to hold the whole story inside it, like a seed. Gauss lived a long life. He became the most celebrated mathematician in Europe, the director of the observatory at Göttingen, a figure so eminent that he was called, even in his own lifetime, the Prince of Mathematicians. He did foundational work in a dozen fields. But he never stopped regarding the 17-sided figure as something special, the discovery of his youth that had decided the whole direction of his life, the thing that pulled the needle toward mathematics on that torn morning when he was 18. And late in his life he made a request. He said that he wanted the regular 17-sided figure carved on his tombstone, the shape that made him. The first genuinely new drawable polygon in 2,000 years, the visible tip of the hidden law, engraved in stone over his grave, so that anyone who stood there would see the thing that had started everything. It was not done. And the reason it was not done is the most quietly perfect ending this story could possibly have, so perfect I almost did not believe it the first time I read it. The stonemason refused, or the plan was abandoned, because of a simple practical problem. A regular 17-sided figure, carved at the size of a decoration on a headstone, is indistinguishable from a circle. The sides are too many and too short and too shallow. Anyone looking at it would simply see a circle, an ordinary circle, and would have no idea they were looking at the shape that had taken 2,000 years to become drawable and had rewritten the boundary of the possible. The mason, the story goes, said as much. It would just look like a circle, and so instead, on a monument to Gauss in his hometown of Brunswick, there is a 17-pointed star, because a star with 17 points, unlike a 17-sided polygon, can actually be told apart from a circle by a human eye. Sit with that, because it is the entire story compressed into a single image. The shape Gauss broke 2,000 years of history to prove he could draw. The shape that decided his life, the shape at the head of that secret diary, cannot be seen as what it is. Draw it perfectly, and it vanishes into a circle. The triumph is invisible to the eye. You can prove it, you can construct it, you can spend 10 years like Hermes drawing an even larger cousin of it, and when you are done, standing back, you see a circle. The gap between what is provably possible and what can actually be perceived, the gap this whole story lives inside, is right there in the stone. He wanted his monument to be the proof of what he had done, and the proof, made visible, disappears into the very thing it was supposed to be different from. They had to carve a star instead, a lie in the shape of the truth, because the truth, rendered honestly, looks like nothing at all. And this is where it stops being about Gauss, or Wantzel, or Galois, or any of them, and starts being about you, about the position all of us are in, standing in front of this. Because what these people found, between them, is a map of the edge of the possible, drawn with a precision that nothing in ordinary life ever offers. They did not find out what is hard, they found out what can never be done, and they proved it, and the proof does not expire. And the shape of what they found is not the shape we expected. We expected the frontier of the possible to be vast, an open country stretching out ahead of us, waiting to be explored by anyone clever enough or patient enough. What they found instead is that the possible is a scattering of tiny islands in an endless sea of the forbidden, that almost everything is unreachable, not for lack of trying, but by the nature of number itself, and that the small reachable region might already be completely mapped, closed, finished, its final entry written on a spring morning before the writer had gotten out of bed. This was never really a story about drawing shapes. It is a story about the difference between what feels possible and what is possible, and about how brutally far apart those two things can be. Your intuition told you, at the start, that you could draw a 7-sided figure with enough patience. Your intuition was not slightly wrong. It was wrong about the deepest thing there is to be wrong about, the boundary between what can and cannot exist under a given set of rules. And you carried that wrong intuition your whole life, because nobody ever handed you the proof, the same way nobody handed it to the circle squarers spending their years mailing solutions to a problem that died in 1882, the same way nobody read Galois until he was a decade in the ground, the same way that diary sat unopened in a drawer for 100 years. The truth about the edge of the possible is one of the hardest and most beautiful things the human mind has ever established, and it is also, somehow, one of the best kept, not by conspiracy, but by neglect, filed away in the professional literature and almost never spoken out loud where you might hear it. And the strangest part, the part I keep returning to when I cannot sleep, and this is rattling around in my head, is the openness at the center of it, the unclosed question. Because for all the finality of the proofs, the impossibility of 7, the impossibility of 9, the impossibility of squaring the circle, all of it locked and permanent, the largest question just sits there, refusing to resolve, whether the reachable island is fully mapped, whether there is a 6th key, whether the catalogue of drawable shapes was, in effect, completed in 1796, or whether it stretches on, secretly, into distances no search will ever reach. 5 keys, none found in 300 years. Probably no more, whispers the mathematics. Probably these 5 are all there are in the whole of infinity. But probably is a word that has no place in a discipline built on proof, and the proof has never come, and it may be that it never comes, that this question outlives everyone alive tonight, and everyone who comes after. That human beings simply cease to exist one day with the book still lying open, maybe finished, maybe not, on a table nobody is left to read. The regular 7-sided figure cannot be drawn. Not by you, not by anyone, not ever. The regular 9-sided figure cannot be drawn. The circle cannot be squared. These are not gaps in our knowledge. They are the permanent shape of the possible, and the possible is much smaller and much stranger than you were led to believe. The teenager saw the first edge of it one morning, and it decided his life, and he wanted that edge carved on his grave, and it could not be, because drawn truthfully, it looks like nothing at all. And somewhere past the last key we will ever find, in a dark that no compass and no computer and no mind will ever reach into, sit all the shapes that were never allowed to exist, named, definable, perfect as ideas, and forbidden, every one of them, forever. The triangle and the pentagon and the 17-sided figure got in. Almost nothing else did, and the door, if it is a door and not a wall, has not opened once in 300 years.